Hi, I'd like to tell you about the force of friction. I haven't done that in my other videos because this was a second-year course, and my students came in already having instruction on the force of friction, but I'm going to add it to the videos. So there's two types of friction. Well, there's more than that, but there's the two types I'm going to tell you about are the kinetic force of friction and then the static force of friction. The static force of friction is just a slightly bit more complex than the kinetic force of friction. Okay, so kinetic force of friction is a force that occurs between two surfaces. We're going to designate it with a lowercase f sub k. The k is for kinetic friction, and some books use a capital F. Just depends on what your teacher wants to use. And this is for friction that where the two surfaces involved are in motion relative to each other, so they're sliding over one another. So let's start out by what is the source of this type of friction. So if you looked at two crates, or a crate and a table, even though they might look smooth like this, let's say this is the surface, let's say this is the surface of a crate, and it looks like the edge is nice and smooth. If we zoomed in and got closer and closer, we would notice that the edge might be like really, at a microscopic level, might be all sorts of irregularities in it. Okay, that's just that microscopically when you go down there, it doesn't look smooth. It looks like it's all jagged in that. Okay, now if I were to take, let's say that's the table. When we looked at the surface of a smooth table, it looks smooth, but instead when we really go down really small and focus on it, it's jagged. And then there's a crate that we're going to put on the table, but if we really looked at the surface of the crate, that also has a jagged edge. Maybe not as jagged. Look at how this is more rough. The table's more rough than the crate, let's say. But now when I put them on top of one another, down is that way. So when I put them on top of one another, you see how they kind of get snagged when they move across, like they get snagged by each other. So it's tough when this slides over. It gets stuck on the nooks and crannies or the peaks and valleys. So sometimes I'll use my hands to show that. Like I'll show a table, and then my other hand is the crate. This hand right here, that one is the crate. And when you put them into one another and you try to push them, you see how they kind of get stuck on each other. So that's what we call friction. Okay, so while one side, if I dragged it across this way, this one will have a force that way due to friction, but this one will have the equal force that way due to friction. So friction, the two frictional forces, there's always two forces because there's two objects interacting, so there's two forces, and one is to the left and the other's to the right. Okay, now if these aren't moving relative to each other, like if I take a book, let's say, here's a book, and I push on the book this way, but it's not moving, but I push on it, then there's some friction on that book, and it's not moving, so that's called static or stationary friction. But if it is moving, if I'm sliding it across the table, then that's kinetic friction. So when it's moving across the table, that's kinetic friction. Okay, so I'm going to first tell you about kinetic friction, where there is motion between the two surfaces. There's motion between the two surfaces, and then static friction is where there is no relative motion between the two surfaces. So there could be motion, like maybe a crate in the back of a pickup truck or something, but the crate and the back of the floor of the pickup truck are not moving relative to each other. So even though the car might be, driving, or the truck might be driving down the road. Okay, so let's talk about this then. We're only going to talk about the force of kinetic friction for this video. So the next video will be the force of static friction. Okay, so for the force of kinetic friction then, we have this equation, It says the force of kinetic friction is equal to a constant called the coefficient of kinetic friction times the normal force. Sometimes the normal force is written with just an uppercase N, but I just write it as F sub N for normal. That's a normal force. Okay, so if you want to calculate what the force of kinetic friction is, it's going to be equal to mu k times the normal force. Just a quick note about this equation. This equation is just an approximation. Friction is actually quite a bit more complex than it's made out to be in an introductory physics course. There's still people are still getting their PhDs studying friction, so there's a lot more to this. This is just like a good approximation to how friction is going to behave, and it's considered to be the force of friction in an introductory class. Okay, so you got this mu k, and the coefficient of kinetic friction is a unitless number, doesn't have any units. It doesn't have newtons or anything like that. And it indicates that the roughness of the surfaces, just how rough are these surfaces. So like this would have maybe a bigger, that's going to tend to have a bigger mu k than something else when combined with another surface. So how rough both surfaces are, and then how brittle the imperfections are of each surface. Okay, so one other point I forgot to make. So if that's my table, if that's the surface of my table, see how that it's going to provide friction. Do you see how if we spill water on the floor and the water fills in these valleys, that now when somebody goes to step down, they're not going to get the friction they were expecting? You see how, like, if we wax over this and fill wax in these spots, you see how that's going to make it slicker? It's going to be easier to slide over. Or a lubricant, like if you put oil in here and the oil rests in here, then the things, when this goes to go in there, it won't get stuck in there. It might ride more on the surface of it and slide more easily. Okay. All right. So back to our equation. So I wanted to tell you about the coefficients of friction then. So you can look them up in a handbook of physics and chemistry, but here's a small table from a textbook. And is that coming in? Not really too well, is it? But you see that they give you a coefficient of static friction and a coefficient of kinetic friction. So there's two of them. They're unitless, and it's always for two surfaces. So this first one, you probably can't read that very well, but it's rubber on concrete. Now, actually, it would even be more specific than that in a table of a handbook of chemistry and physics, and they would tell you like a very particular type of rubber and a type of concrete, and if the concrete's wet or what have you. But these are just basic ones: steel on steel, aluminum on steel. You see how it's always two things? It has to be two surfaces. It's not. You never have the coefficient of friction for one surface. It's for two surfaces that are going to be interacting: Teflon on Teflon, ice on ice. Okay. Notice that the coefficient of kinetic friction is usually less than the static friction, and there's a reason for that. I'll tell you in a moment. I'll tell you in a moment. Okay, so let me tell you that now, because I'll forget otherwise. So it just makes it easier to break these off. When something slides over something else, they get stuck, and then they break, and that's called wear. Like when things wear out, like if you just took a book and you scraped it across the table for 10,000 times, the book surface would wear out, and that's because it's breaking. The two things are brittle, and so it turns out that it's easier to break those if you get a running start. It's kind of like if you were going to try and get past some people that were trying to stop you going someplace. Would you rather get a running start to get by them, or would you rather just try and push your way from a stationary position? And it's just easier to get a running start. Now, you might say, hey, doesn't friction also depend on how fast it's moving? And it does, but that's why this is an approximation. That's one of the reasons it's an approximation. There's a bunch of reasons. Okay, so let's see why this equation makes sense. So this equation is going to say that to find the force of kinetic friction, it's only two things. It's the coefficient of friction, which is describing, it's a unitless number that indicates how rough the two surfaces are and how brittle they are. Yeah, so the rougher the surface and the less apt they are to break, the nooks and crannies are to break, the bigger this is going to be. And then this is multiplied by a normal force because it's how much it's squished together. So the two surfaces, if the surfaces are lightly interacting, then it's easier to move than if you squish them together. If you really squish them together, see how my fingers are like stuck now? Like it's a lot harder to move. Let me give you another for instance of that. Let's go back to this book. What happened in my book? There it is. Okay, so right now it's pretty easy for me to push this along the surface of the table. It's pretty easy for me to push that. But could you imagine if somebody stood on this book, or you came and you pressed down on the book? If I did that, if I press down, I'm not pushing that way, I'm just pressing down. If I press down in the book, it's a lot harder to push this book across the table because these nooks and crannies are now crushed in there. So that's why the normal force is an important part of this. So the more they're crushed together, the more the frictional force. Okay, and you just multiply those together. So the normal force indicates how much the surfaces are squeezed together, how much force they're squeezed together with. Okay. All right. There's always two normal forces for when you have two surfaces, but you only use one of the normal forces. The other one will be the exact same normal force, but in the opposite direction. Newton's third law. Okay, so let's see how this applies to like a really basic problem. So I'm already at 12 minutes, so let's get this done here. So imagine you have this surface of a table that has some friction on it, and it's completely horizontal, this table, and there's a crate that was pushed sometime in its past. It's pushed and it's moving to the right. It's 2 kilograms. And it's going to slide to a stop. But as it's sliding to a stop, we want to know what its acceleration, what the crate's acceleration is going to be. Because if I know the acceleration and the velocity, I can figure out like how long it's going to take to stop and how far it's going to go and all that stuff. Now let's say the coefficient of kinetic friction is 0.20. Notice that doesn't have a unit. Okay, now if I want to get the acceleration, which then would allow me to get a bunch of other stuff, I'm going to use Newton's laws. So what I'm going to do is I'm going to first draw a free body diagram of this. Okay, so the free body diagram of this crate is going to look something like this. There's a force down. Now I'm using G as 10 meters per second squared. I know it's closer to 9.8 meters per second squared, but I'm just going to say that M times G is 2 times 9.8 meters per second squared is about 20 newtons. Okay, so that's the force of that's the mg. That's the force of gravity, and then there's a force upward on the box, a normal force upward on the box of it's got to be 20 newtons because the box isn't going to go up in the air. It's not going to come down. So because I know it's not accelerated in the y direction, I know that the normal force has to equal the force of gravity. Okay, now there's one other force on the crate, and that is as this crate, here's the table and here's the crate, and it's sliding that way. This crate is sliding that way. See how it's getting caught up in the nooks and crannies as it goes? So it's sliding that way. So there's going to be a force to the left. Now, there will also be another force to the right on the table that will be equal to this, but we don't care about that. So this is the force, oh, I messed up. It's going to be the force of kinetic friction. So it's, boy. I'm going to say it's F sub K. Okay, so I want to know what that is. Okay, so so if I know that force, then I can easily do Newton's second law, because these are going to cancel, and so the net force on this is going to be the force of kinetic friction. So I can easily get then since I know the mass, I can easily get the acceleration. All right, so let's do that. I'll put that in orange. So the force of kinetic friction, perfect, is going to be equal to mu k times the normal force. So the force of kinetic friction is equal to mu k 0.20, no units, times the normal force. Now the normal force is 20 newtons. One more time, just to say this one more time. This number is describing how rough these surfaces are and how easily broken the nooks and crannies are off of those. Okay, that number is gotten experimentally. And then this number is just how much these surfaces are squeezed together. And so the more you squeeze them together, the more friction. So when I do this, this is going to be the force of kinetic friction is going to give me 4 newtons. So it's 4 newtons to the left. Okay, so that's so now to get the acceleration, A equals F net over M. So A is equal to F net, so it's going to be 4 newtons all over 2 kilograms. So that's 2 meters per second squared. Okay, now I need to let you know then that it's to the left. Where'd that negative come from? I just throw that negative in there. Where's it coming from? It's because the force of kinetic friction is to the left. So it's really to the left and to the left. Okay, a couple things about direction. And so I'm done talking about this, but I want to just say a couple things about the direction of the force. And so if you don't care about that, then you can end the video right now, because I've been talking a long time. But just a thought on the direction of the force. The real equation is really this: is the force of static friction, the magnitude of it, is equal to mu k times the normal force. And the reason why you have to say that is because it's the magnitude of this. Because this direction of the normal force is not the direction of the force of static friction. And so if you just multiply a scalar quantity times a vector quantity, you get a vector when you do that. And it's in the same direction. What you get, that vector will be in the same direction as this, unless you state it like this. Okay, so like F net equals MA. So F net equals MA. Those are vectors. Mass is a scalar, but so this vector and that vector are in the same direction always. The acceleration and the net force are always in the same direction, because we didn't do this to it. So yeah, that's just a technicality. One other thing about this is the force in our last example. There were 3 forces: the normal force, or the force of gravity, the normal force, and then the force of friction. And I just wanted to say one other thing about that, the force of kinetic friction. We artificially break this into a normal force and a force of kinetic friction. Both of these are really the table pushing on the crate. And so we just artificially break it into one that's straight up and the other that's to the left. But the table, if you ask me what direction the table's actually pushing when it's sliding across, it's you know, the normal force is up, because that's the definition of normal force, is it's perpendicular to the surface. And kinetic friction is that way, but the table's really pushing, you know, like somewhere in that direction then. And that's just a finer point. Okay, I'll see you for our next video on static friction. Thanks. Bye.